Welcome to Lecture 10 of Introductory Astronomy. Today we're going to be going into the outer solar system. We're going to buzz through these big planets and go out to where we're not quite sure what's going on, the edge of our knowledge of the solar system, and things are happening there at a fast rate. Here's something though. As we fly out the outer solar system, we're going to pass through the regular inner and middle solar system and see things like this. This was an unexpected sight, and we will learn what this is today. I heard before that it could well be, one hypothesis was that it's a kitty litter. And we can guess what the kitty litter is clumping on. But first, here we are with the famous slides that everyone now expects and wants. This is PH1600, for lack of a bureaucratic number. Lecture 10, we'll be talking about Pluto. We've heard a lot about it. Pluto's been Plutoed, as you know. Dwarf planets, what are they? And asteroids, which is a bit of an outdated name, but everybody knows of it. So next lecture, we're going to talk about comets and meteors. Next week, we're going to probably, I'll confirm this, check my schedule, not have classes so that you can take the midterm. I believe a week from today, the midterm will be released. And will be due several days later. I'll have more information on Wednesday. But there will be a quiz on this week's stuff. This is Michigan Tech. I am this person. Here's where you go to get credit. So, once again, I need to put this in every lecture in case people don't get it. What you're responsible for, this lecture, the listed Wikipedia entries, but not the higher math, the astronomy pictures of the day, and the way you get credit is by taking quizzes in the midterm and the final. So 1 to 4 should already be due. 5 will be due soon. Actually, there was a glitch in 5 being released, so 5 is actually going to be extended longer than before. Still, many people have taken it, but it's going to be available longer. Go here to find out more. So the Wikipedia entries you'll be responsible for today are Pluto. Actually, now that I see minor planet, I should have had another term, which is dwarf planet. Minor planet's going to take you to asteroid, actually. So make this DWARF, dwarf planet. Let me write it again. Dwarf planet is what you're responsible for. And here are some dwarf planets: Ceres, Haumea, Makemake, and Eris. And they all need the dwarf planet designation to get to the right Wikipedia entry. Otherwise, you might be taken to a god or goddess in folklore. Pluto, we'll find, is also a dwarf planet, but it's famous enough so that when you search for it on Wikipedia, you can get taken there just by typing in Pluto. Then we'll talk about asteroids, in fact. So dwarf planets are a recently created designation. So things are happening fast in the past few years here, and even in the past month or two. The International Astronomical Union, a group of astronomers, which may or may not have this power, has decided to create a category called dwarf planets because people weren't happy with Pluto. And things were being discovered that were like Pluto, and so there was some problems. What do? Do you make these new things being discovered planets like Pluto is, or do you demote Pluto? Now, even before these extra outer solar system objects were discovered, people had realized that Pluto wasn't really like the other planets. It hadn't cleared out its neighborhood. It was not very big. The two more innermost planets on the average were Uranus and Neptune. Jupiter and Saturn were clearly much bigger. Pluto was on the small end of things and seemed kind of diminutive. So there was a question as to what to do about it. And the IAU voted in 2006, although there was a commission that looked at this, and then the vote came to a surprise to me because even a few days before it looked like that Pluto would remain a planet along with Ceres and other things. But no, they created dwarf planets, and Pluto was the first one. So the criterion they gave for the whole category of dwarf planets were that they had to be spherical. They had to be massive enough to pull themselves into something like a sphere. They had to orbit the sun. as opposed to orbiting another planet. So the Ganymede, which may be bigger than some of these things, doesn't get planet, even though it's spherical, because it orbits Jupiter. Arguably, if you were to pull Jupiter away, Ganymede and the other Galilean satellites would still orbit the Sun, but they primarily orbit Jupiter. So if you were to pull the Sun away, the orbit of Ganymede wouldn't be much different. But if you were to pull Jupiter away, way different, but still around the Sun. This is a debatable criterion, which is there's papers going back and forth between astronomers as to whether this is an important one or not. It sweeps out the material in its orbit. So Jupiter, clearly a planet, doesn't have any Jupiter-sized objects orbiting the Sun near it because it's deflected them all. Same with Saturn, but not true, one might say, of Pluto. So this is criteria for a planet, by the way, for a full planet. So Pluto had a problem with the third one. It was mostly spherical. It orbited the Sun, but it didn't sweep out its orbit. So in this dwarf planet category, there are now 5 entries. Pluto was declared one. Ceres, which is actually in the asteroid belt, not out in the distant solar system, was one. Eris was voted one, and then 2 were voted in the past couple of months. They were discovered in the years before, in the past few years, but the International Astronomical Union, IAU, made them into dwarf planets just in the past couple of months, Macae, and Haumea, and we'll be talking about what they are. So another advertisement for this course. If we were taking this course out of a textbook only, we wouldn't be able to talk about Macae, and Haumea, at least as regarding the textbook. But since we're going off of Wikipedia and APOD, both of those web-based information sources are rapidly changing enough to keep up to date, even on the daily time scale. So this course is modern enough to include that. Whereas if you were to take this at your local university, if they focus on a textbook, they wouldn't be able to get that information out of a textbook. It's too rapidly changing. This is an old, by this point, slide taken in 2006, again trying to tell you how fast things are changing. Here, there were now 8 planets which hold today, Neptune being the outermost planet. There is Ceres. There's a little spot here, hard to see. Ceres is an asteroid belt. It is now a dwarf planet. Pluto is a dwarf planet. At this point, Eris, I think, was called 2003 UB313. The important part of that, or one of the important parts about it, 2003 is the year it was discovered. So we're discovering these Pluto-type things out in the outer solar system. How come we couldn't do it before? Well, we have modern technology now. We have automated telescopes, but more importantly, we have computers that can sift through lots more images than the human eye can. So when Pluto was discovered 50 years ago or so by Clyde Tombaugh, he had to use a blink comparator with his own eye to find that Pluto had moved. But now we can just take lots of pictures. Not only that, but these images are usually out of the typical plane of the solar system, the ecliptic. So they're out there, they're at a different angle, and they're looked at very quickly by a computer, and the computer picks stuff up and says, what's that? This thing it's a transient in some sort, in that it wasn't this picture and it wasn't in the previous picture. And humans just can't look at that many images. But not only that, it can find it moving. It's here now, it's here, then it's here, then it's here. And so then it kicks it out, and it's not fully made by a computer, but when it sees something like that, it tells a human, go look at this is strange. And it could have been an asteroid belt object. But if you follow it long enough, you can get the orbit, and you can say, hey, this is in the outer solar system, and you find things like Pluto, bigger than Pluto, out in the outer solar system, usually a little bit outside of Pluto, but sometimes near the orbit of Pluto. So Pluto wasn't alone. Pluto was found because it was pretty near the, although it's out of the plane of the ecliptic a little bit, it wasn't far enough out to be missed. So where are these asteroids? And, well, asteroids are called minor planets. Dwarf planets are the biggest of the minor planets. So the biggest compository of comets, and I would guess asteroids, would be the Oort cloud. Now, the comet is essentially an asteroid that is seen to have a tail at one point and a coma, which is sort of We'll find more out about that next time. A gas cloud around it. So these things visually define a comet. Astronomers have many times said, oh no, asteroids are way different. Asteroids are rocky and comets are icy, but we've found that that's not necessarily true. The biggest distinction is visual. Comets look comet-like. They've got a coma, they've got a tail. Asteroids don't. Typically, comets are found when they come in near the sun because the sun melts them off, and then the gas makes the coma, makes the tail, makes it obvious. Asteroids typically don't swoop in that close to the sun, also called asteroids or minor planets. So where are all these things coming from? How do we get new comets? Didn't we discover everything in the solar system that we could possibly discover? Turns out no. Turns out there's an Oort cloud out there, way out there, discovered by, strangely, this guy Oort, Jan Oort. And this thing might have billions of comets. And these things have been slightly perturbed by our sun, our solar system, moving close to other stars, having tidal effects possibly from our galaxy, things like that. And some of these guys are just given a very slight push. And that causes them to fall in toward the sun. And eventually we see these things. Now, outside the orbit of Neptune, around Pluto, there's another belt of comets that isn't so many, and we don't know how many, and it's actually controversial even given today's standards. There's been a paper that's just been circulating in the past couple weeks that says that the Kuiper belt doesn't have all that many objects, but it might have hundreds. Members of the Kuiper belt are these new dwarf planets. So we're discovering what's out in the outer solar system, out past Neptune. And with computer technology, we're discovering it now. We live in the age where we're discovering the outer solar system. Earlier on, with the human eye, we could see the major planets. So discovering Saturn, it predates written history. People always knew that Saturn was there. Then with the age of telescopes, one could discover Uranus, although we found out that Uranus is just barely visible with the naked eye. Then Neptune, then Pluto. These are the age of the small telescope enabled us to do this. The age of the computerized telescope has now opened up the outer solar system even more, and we're in that age right now. So this is our busy solar system. The planets get all the press, but this is the asteroid belt. Oh, also, the age of the telescope opened up the asteroid belt. Found out there's lots of dim things orbiting that aren't very massive. So this is Mercury's orbit, this is Venus, Earth, Mars, and Jupiter. So you see that between Mars here and Jupiter here, there's the main belt of asteroids. It doesn't mean that's the only place that there are asteroids. No, there are asteroids actually all through the solar system. Little bits, but there's just not concentrations of them like there are in the asteroid belt. That's the main place to find them. Besides the asteroid belt, the Kuiper belt has, I guess, asteroids too, and then you have to go out to the Oort cloud to find even more. But even between those things, it's not barren of stuff. There's just less. Every now and then, one of these things is caught by a planet, and we think that Phoebe, one of the planets, one of the moons of Saturn, was caught. So let's look at Pluto. Gets all the press. Discovered in 1930, so I was wrong about 50 years. It was almost, 80 years. However, recently, with better telescopes and monitoring, we've been able to find that it has a moon, Charon, and even more recently, 2 more moons, Nix and Hydra. Now, Pluto is smaller than the Earth's moon. Its radius is about, it's 2/3 out of the Earth's moon. Its radius is about 1,200 kilometers. It orbits about 30 to 50 astronomical units. An astronomical unit, as we know, is the distance between the Earth and the Sun. Usually, Pluto is outside the orbit of Neptune, but not always. Before 1999, for several years, it was actually closer than Neptune. It takes Pluto 248 years to orbit the Sun. Pluto is composed of rock and water ice, and it has a very thin nitrogen atmosphere. It is an unusual object, and we discover some more about it all the time. This is Pluto in what was told to me is true color. It is a world that has surface features that we don't know about. Because of the objects that used to be known as planets 10 years ago, the only one that has not had a spacecraft zip by it is Pluto. So we don't know. It's this fuzzy mask. These squares, they're pixelations. They're not real. Pluto doesn't have squares like that. That's just like our monitor showing us that. And sometimes for APOD, the pixelation actually looks kind of cool. Gives the eye the fine detail that it craves, because the eye doesn't like fuzzy things, we've discovered. If you look at something fuzzy, people find it annoying. But if you actually pixelate it and make nice, sharp pixels, then people get the idea that we don't know higher resolution because people are used to looking at pixels on monitors, but yet it's somehow more pleasing to look at. So hopefully you'll be pleased to look at this true color view of Pluto. Now, the reason why we know about the things on Pluto isn't necessarily because we have high-resolution telescopes. Pluto is so small that we can't really map it with telescopes. But what happens is Pluto and Charon eclipse each other from the Earth. And so watching very closely how bright they are when they eclipse each other tells us gross surface features. So here we can see there are a little dark area there and bright area there and a big dark area on Charon there. So more than that we don't know, but we do know that it's not just a uniform body. So even this commonly phrased object, Pluto, is mysterious to us. We're still discovering more about it all the time. So here is an image, I think, in 2006. Here we see Nix and Hydra, two smaller moons of this thing that's roughly the size of our moon, a little bit smaller. Here's Pluto and Charon there. This, I guess, was taken with the Hubble Space Telescope. So let's go visit Pluto, the only thing that used to be known as a major planet that hasn't been visited. So here is the launch of the New Horizons spacecraft, zipping up. Became, I think, one of the fastest, if not the fastest, man-made object relative to the Earth, really zipping out there toward Pluto. It's only going to buzz Pluto, though, and then it's going to go to even further Kuiper Belt objects. Which ones? Well, they're still under debate somewhat, but so we don't know exactly which ones it'll be. But this has already, even though it was launched in 2006, it has already buzzed Jupiter. Okay, I will now take a brief aside. It is useful to know something more classically taught in astronomy classes, which doesn't have very beautiful pictures associated with it. It was discovered hundreds of years ago by Johannes Kepler, and they are known as Kepler's 3 laws. And they were very important for Newton discovering his universal law of gravitation. So Kepler's 3 laws, in this boring aside, and we will get back to fun stuff in a bit, is the first thing that Kepler noted was that planets orbit in eclipses. So let's even do an aside for an aside. How is it that Kepler knew to do this? Was Kepler just so much smarter than everybody? Well, Kepler was one sharp guy, that's true. But he had something that is key to discovering things, and that is better data. So there was this guy, Tycho, who happened to have come into some money, and besides having a silver nose, went out to a planet and started measuring the positions of planets. And I mean the planets, because they didn't really know about dwarf planets back then. He started measuring the positions of planets really, really accurately and recording them. And some people would consider this boring. But he was really good at it, and he had people who worked with him out on this island that were really good at it. And so one thing is that Kepler got access to this really accurate data. And with that really accurate data and being really clever, having those 2 big advantages, he was able to come up with his 3 laws. And one was he realized that planets don't orbit in circles or even circles on circles. They orbit in ellipses. And the sun is at one of the focus of this ellipse. So here's a picture of it. Here is a planet. This line is meaningless. Here is the sun. So the planet is going to orbit the sun. So one question I frequently get is, well, what's at the other focus of the ellipse? An ellipse has 2 foci. And if the sun is at one, is there like another sun at the other one that we don't know about? And the answer is no. If there was another sun there, it'd light up the solar system. If there was some dark thing there, we'd see it because people are curious enough to look there. It turns out with if you know Newton's law of gravitation, F is equal to g mass of one object and mass of the other object over r squared. It naturally maps out ellipses anyway without anything being at that focus. All you need is to have something at this one. In fact, if you had something at that one, it would make things messed up a bit. But going back to Kepler, he figured out that these things are ellipses. Ellipses were relatively well-known geometric figures, so that was good. They're more complicated than circles. Lots of people were pulling for circles because circles are really simple. Now, ellipses are much more complicated, but they're still well understood. Well understood mathematics underscores an ellipse. The next thing Kepler discovered was that the planets don't go around the ellipse at the same speed. No. It turns out that when the planet is near the sun, or the point on the ellipse that has the mass, it goes much faster. So this is going zip, zippity-doo-dah here really fast and really slow out here. So I have a, okay, so here's an image of that. So in one band of time, a planet goes from here and here. It goes really fast. And when it's far away from the sun, say, here, it's not going so fast. It only went this far. So here, in that one period of time, went here. And so how do you know how much it did? Well, you can figure it out if you were Newton, and you know Newton's law of gravity, but Kepler predated Newton, so he didn't know that. But what he was able to figure out was that this area here is actually the same as this area here. And Newton, of course, read what Kepler had done and used that to help him come up with his universal law of gravitation, which, as we heard, was F equals gmm over r squared, which we still use today. It's the most accurate law of gravity we can typically use in the solar system. Now, Einstein came up with an even more accurate general relativity, but to use it, it's messy and complicated. And you don't get almost any accuracy increase in almost every circumstance over Newton's law of gravity. So Newton pretty much solved the solar system with that one. And he stood on Kepler's shoulders. And Kepler's second law was that equal areas and equal times. So going back, the third law is that the period, which is the time it takes for a planet to orbit, say the sun, or a moon to orbit a planet, is proportional to the radius. Now, we just said they're ellipses. But now let's say, okay, in the solar system, most of the ellipses are pretty circular. So let's assume they're circles. And if you can actually, you can get around it by saying this isn't the radius of the circle. This is something called the semi-major axis of the ellipse. So it works for ellipses. But for visualizing in this class, let's say that they're circles. Now, how do we know what this means? Okay, this enables you to estimate how long it takes almost anything in the solar system to go around the sun. So let's say the Earth has a period of 1 year. And then this is mass of the sun, so that's one solar mass. And this radius is 1 Earth-Sun distance, which is AU. Now let's say we want to find something that has twice the radius of not the Earth, but the radius of the orbit of the Earth. Let's say it's 2 AU. How do you find out its period? Well, you cube it, and you make 2, 4, 8, and then you take the square root of 8, which is what, almost 3, 2 point something. Let's say 2.8. So 2.8 years would correspond with 2 AU. So that's how you do it. So this works so long as you're always using the sun. So now, whenever we see something, and we'll come in the future slides here in today's lecture, we'll see things out in the solar system we can compute based on how far out they are, how long it takes them to go around the sun. So with Kepler, we came to a much better understanding of the solar system. Okay, now on to modern times, and this is Ceres. So Ceres is about a kilometer across, and as you see, how big is that? So here's Earth's moon, and here's Ceres, and here's the Earth. So it's the classic picture of the Earth, the big blue marble, and the moon is smaller, but still comparable in size in some way to the Earth. Ceres is smaller, but Ceres is still a sphere. It's actually getting close to, if it was much, much smaller, it wouldn't have enough mass to pull itself into a sphere, but it is still a sphere. So here's the best we know of it. Now, if Ceres was a planet, then we would have sent probably a spacecraft by it, and we'd have these really cool pictures of it with all kinds of craters and probably grooves or whatever it would have. But we don't know, because it wasn't popular, not getting a lot of press before the past few years. So it's got a bright spot. That's what we know. It's got a pixelated bright spot. But hopefully, with all the new impressive, it's the closest to dwarf planet. Given that designation, we're hopeful, and I've already seen things come across, people suggesting missions to go past Ceres. I would say probably in the next 20 years or so, we'll have something that zips by it, and when your kids take an astronomy course, they'll say, oh, did you see that really cool picture of Ceres? It's on the test or the quiz. Okay, where is Ceres? Ceres is in the main asteroid belt, so it's not out in the outer solar system. So where's that? So here is the Sun, here's Mercury, here's Venus, here's Earth, here's Mars, and then in a reasonably circular orbit, there's Ceres. Here you see in the lower one, the plane of the solar system, the ecliptic, and Ceres is tilted with that plane. And it's out between Mars and Jupiter. So here we see that Ceres has about 2.9 AU. That's its distance from the Sun. So distance from, well, no, it's about 3 AU from the Sun. So my question is, if it's about 3 astronomical units from the Sun, how long does it take to go around? So let's do that. So let's see, period squared is about radius of the orbit cubed, right? So let's go back and check that with Kepler's law. Yep, there it is. So now we know that the radius is 3 cubed. So period squared in years is 3 cubed. So what is 3 cubed? 3 times 3 is 9. 3 times 9 is 27. So that's 27. So now we take the period in years has to be about the square root of 27, because this was squared. So let's see, 4 squared is 16, 5 squared is 25. So it's more than 5. 6 squared is 36, so it's just more than 5. So actually, strangely enough, it's working out to 4.5 years. I guess that might be due to the ellipticity, the eccentricity. 3, 9, 27. So, okay, so it's on the order. So I'm actually a little confused as to why it's not closer to 5, but we'll check into that. Another large object in the asteroid belt is Vesta, but Vesta is not massive enough to be spherical. These are pictures taken by the Hubble Space Telescope. They're just fuzzy because the Hubble Space Telescope doesn't have the resolution to do better. Now, the James Webb Space Telescope that should be launched in a few years, it will probably do better than that. But it will still be somewhat fuzzy. So, what's going on in the outer solar system? It's been advertised. Here it is. So, now, the largest object in the outer solar system is now Eris. It has a moon, Dysnomia. The next largest object known currently in the outer solar system is Pluto, this famous thing that used to be a planet. And it's got a relatively large moon, Charon. Most recently, there have been 2 more designated as dwarf planets of the outer solar system, also known as trans-Neptunian objects, because they're outside the orbit of Neptune. One is Makemake, which is big enough to be a sphere, and the other is Haumea, which has a moon, but strangely enough, 2 moons, but it isn't a sphere, but we think it's got enough gravity so that perhaps if it wasn't spinning or something, it could have been a sphere. It might be rotating. I actually am not exactly sure why. It's an ellipsoid of revolution, apparently. Now, there are 4 objects out there that are even smaller. So why Haumea is a ellipsoid is still a bit of a mystery, I think. 4 more objects at least, and more being discovered: Sedna, Orcus, Quaoar, and Varuna. And 2 I've heard about relatively prominently, Sedna and Quaoar. Orcus and Varuna, not well known. They appear to be spheres. They may be nominated into or promoted into dwarf planet status. But right now, these are the dwarf planets as of today. And along with Ceres. And these are not yet. Not yet, in question mark, dwarf planets. Now, the International Astronomical Union is not done debating what's a planet, so it's quite possible at their next General Assembly, which I believe comes up this summer, there might be a new vote. And what happens then? Don't know. Could be that Pluto is reinstated and these could all become planets up there. Okay, so here is Eris, the largest known. This is all we know about it in terms of what it really looks like. And here's its moon, Dysnomia, I think it is. So we're just seeing them. We're not picking out features. We're just finding them on the sky at this point. So Eris is on a very inclined orbit. Here's the plane of the ecliptic where the planets typically orbit. Eris is way up there in terms of altitude. Pluto's a little bit, as you can see, but Eris is even more. Okay, most recently in July, so who remembers where they were in July of this summer? The solar system changed, and Makemake, which had been discovered a few years before, I believe about 3 years before, was promoted to a dwarf planet. So Makemake is now a dwarf planet. It's in the outer solar system. I'll show you where it is relative to the other ones. Dwarf planet. Okay, here is an artist's rendering. This, by the way, this is an artist's rendering of Makemake. We don't know what it is. So what we do is we hire people and say, oh yeah, it's about this color. Who knows? Probably a sphere. Could have craters, not sure. Probably does. So then they draw it. So we don't know. I would guess that Haumea also has craters, but we don't know of any. So it's drawn right now without them. And since this course started, this is how fast astronomy is changing. Since this course started, Haumea has been voted by the International Astronomical Union, has been promoted into a dwarf planet. Known for a few years before that. So here we see some orbits. Red is Pluto. I believe this is the plane of the ecliptic here, where all the rest of the planets orbit. So Pluto is out here, but we see that Haumea and Makemake, they're not that far. They sometimes go closer than Pluto. So if Pluto was to be here and Makemake was to be here, Makemake would be inside the orbit of Pluto, but more inclined. Haumea also sometimes comes inside that too. So they're all three out in the outer solar system, and it takes long, many decades for them to go around the sun. So here you see 1991, it was on this side of the orbit, and in 2133, so in more than 100 years, it'd be on this side of the orbit. Here's how these things are discovered. Once you see them, you can flash them, and then they become obvious. This is Quaoar. Sorry. These things I don't hear pronounced too often since they're so new, so my pronunciations might change between classes. So they're discovered by computers that see exactly that, and then they show the humans, they print it out. All of these things, these are stars. They don't move. Stars don't move relative to each other, hardly at all, over the time scale of months to years. But if you see something moving in front like this thing, I'll go previous next so you can see it move again. Here you see it moving in a straight line. You've got the 3 images, so that's good. Once you get some more, you can start determining its orbit better. And once you look at it over the time scale of a year, you can get parallax on it and get its distance. And it's not a star. Just with 2 images, it might have been in the asteroid belt. But once you get a bunch of them over the time scale of a year, you can start seeing that you have much smaller parallax than the asteroid belt. Okay, so let's talk about asteroids. As I said before, they're all over the solar system. But most of them are in the asteroid belt between Mars and Jupiter. There's a visual distinction. They are confused with comets. There's a visual distinction in that, as I said earlier in this class, they show no tail or coma. Ceres is an asteroid in the asteroid belt. They're also called minor planets. I find the term minor planet uninspiring, personally. Asteroid's cooler. It's also a better video game. Also, more people know the term asteroid than minor planet. And with dwarf planet coming and going and minor planet, I confuse them sometimes. So, rogue that I am, I will keep referring to them as asteroids. Apollo asteroids are particularly interesting because they cross the orbit of the Earth. That means that maybe one day they could hit the Earth. Well, who cares? Well, something small hit the Earth in the Tunguska event in 1908. And the people who live nearby, they cared a lot. Because I don't know if anyone was killed, I don't think so, but like the sky lit up and trees were knocked down, and it was the equivalent of a major nuclear explosion. And that would be relatively minor, unless it hit a big city. The big problem with Earth-crossing asteroids is if they hit the Earth, and particularly if they hit the ocean near a seaboard where there's a city, then there could be a large tsunami, huge waves that go and annoy the city, destroy the city. We've had a big tsunami about a few years ago. Did anyone see the video of that? It was a horrible tragedy. It wasn't fun. So in the Upper Peninsula of Michigan, however, were something to hit a major ocean, we'd be okay because we're in the middle of North America. No tsunami is going to come out into the middle of North America. If it hits Lake Superior, it could be a problem, although Lake Superior doesn't have as much water as an ocean. But cities on major seaboards, which are many of the major cities of the world, like New York, like Los Angeles in the United States, to name a few, they might get hit by a tsunami and they could be damaged by it. So one of the major pushes in modern astronomy is to find the Earth crossing the Apollo asteroids and as many rocks as we can that would be a threat. And then what do? Well, just knowing about it would be useful. Because if we knew that something was going to hit near a seaboard, we could move the people away from the seaboard and they can come visit us here in Houghton. However, that is a logistical problem. It might be easier to try to deflect the asteroid or rock before it hits our Earth. We'd have to know its orbit very carefully. So typically when we discover something out that has a possibility of the Earth, we don't know. The Earth is in its target. So all we know is roughly going to hit here. Here's like a 90% probability inside of that, 60% inside of that, and the Earth is here. So it might get hit. But we don't know the orbit well enough to tell. There's significant error. So once we determine that it's on possibly an Earth-crossing orbit, then we start pulling out the big telescopes, looking at it as much as possible, trying to determine the orbit better and better. No known rock is on a collision course with Earth that could cause danger. There are some that we're still in the fuzzy possibilities of, but don't worry about it. Don't buy asteroid insurance at this time, because we're probably not going to get hit by any of the ones that we know. But it's the ones we don't know. It's the ones that you don't know that get you, right? And that's the same true with these rocks. So we need to discover more of them because we don't know all of the ones that hit the Earth. And there's a possibility that if we were to discover it enough, and if we were to know its orbit well enough, we could deflect it. And there's people who come up with clever ways of deflecting asteroids. One is to try to zap it with a laser. Now the laser is going to have relatively little power and is not going to be able to push the asteroid by itself. But if you could melt a hole in it, you could open a cavern where it outgasses, and then the gas that comes out of the cavern, maybe that will deflect it. And all you have to do is deflect it by a little bit if it's way far away from the Earth, and that's good. These movies with Bruce Willis in them, I enjoy watching the movies, and I enjoy watching Bruce Willis movies, but they're not realistic, because if the asteroid is already a couple diameters of the Earth away, then we're going to get hit by it, because the amount of energy taken to push it away at that point is tremendous. And we don't have that kind of energy, not even in nuclear weapons. And what's worse, if you blow up the nuclear weapons and it's only a couple of Earth radii away, you're going to make it into a fragmentation bomb, right? It's still going to hit. It's now going to hit lots more places. Maybe we would have been better off if it only hit one place. So it wasn't a good idea to set off the nuclear weapons on the asteroid when it's only a few Earth radii away. No, not a good idea. The best idea, it makes less good Hollywood movies, is to try to deflect it when it's really, really far away in its orbit. Okay, back here on Earth, where we're safe so far, There's lots of Kuiper Belt objects that are continually being discovered. There are probably going to be other dwarf planets promoted and discovered because we're in the exciting era where we're seeing these dim things with computers and being able to pick them off. Okay, there are other asteroids out in the solar system, and they are not as big, and they are not on Earth collision courses. Many of them have been flown by spacecraft on the way out to planets, or things that were planets when the spacecraft were launched, like Pluto. So here we see the Galileo spacecraft, which was on its way to Jupiter and did a great job near Jupiter, passed by Ida and Dactyl, an asteroid and moon. And my notes tell me that this is about 50 kilometers, which is much smaller than the 1,000 kilometers that we're seeing in the really big objects in the outer solar system. So this is a little dinky guy. And another way you can tell it's dinky is because it's not a sphere or even close to a sphere. Has lots of craters on it, though. The next one, Gaspra, 20 kilometers. 20 kilometers there. Not really blue, just the colors are exaggerated here. So these are thought to be essentially a large rock. This is a big rock. But not everything we see. Well, here's another one. Here's another large rock. This one was seen by the NEAR spacecraft, which was on the way to Eros. And before it got there, it passed by Matilda. And it saw this one. 60 kilometers across. So again, much smaller than the 1,000 kilometers of the outer solar system. This is Eros. And this is what it looked like. It was a bigger rock and unusually shaped, not massive enough to form a sphere, huge craters, and we got lots of good images of Eros by the NEAR Shoemaker spacecraft that went up to it and even landed on it. And here it is going around the limb there. Really cool image. Really gives you the idea of being there. And so NEAR Shoemaker sent back lots of images which were made into a movie. Here it is, only I think 60 kilometers away from, this is a color image, so you can see what's called the regolith, which is the dirt and rocks that accumulate there, which turn out to be important because we're finding things now, as we saw from some of the moons of Saturn, that sometimes the regolith smooths over the craters. And some of these things are thought to be just big, what's called rubble piles. So we picture them as this big rock. And if you could pick it up and turn it over. But they might not be that way. Some of them are just lots of smaller rocks just all put together. And so if you tried to pick it up, your hand would just go through it and you'd crush the rocks and you'd push the rocks away. It's not a solid body in any easy sense. However, there might be an intermediate ground where there is a solid core, sort of, but the out part of it is a regolith, is a rock pile on the outside. So here is, they actually, at the end of the mission, they landed it on the asteroid. So this is a few meters, 130 meters above the surface. This is what Eros looked like just before it crash landed into it. Actually, I think it survived the landing. They weren't sure it would. Then we started getting more bold, and we started smashing things into some asteroids. So this is a comet, actually a comet, Comet Tempel 1, an extremely loose pile of debris, we learned. And in order to find out more about it, the Deep Impact mission released something called an impactor. And the impactor went down and smashed into it. Now this was known, was known to be a comet because it has these things blasting gas and stuff, so it had a coma at one point. After the impactor hit a few years ago, I think in 2005, this is an image. It was actually quite bright. Here is the, oh, it's off the top, I'm sorry. 30 seconds after impact, it says. So you can read more about this in the astronomy picture of the day for July 5th, 2005. The impact, the whole mission was a great success. They were wondering, they didn't know for sure whether it was a rubble pile or not. They dropped something, it was really bright. And then they were able to take images after it. And here's a picture of the surface. So it is thought that the impactor went inside and Comet Tempel 1, and I think it impacted near this site there. And here you can see it has craters, and it's just an unusual asteroid as we're trying to find out. In 2005, later that year, the Japanese sent a spacecraft, Hayabusa, to Comet, what's the name of the comet? Itokawa. Itokawa. And this was not a well-publicized mission in the United States, but once the images came back, it became well-publicized, because this is one of the strangest looking things anyone's ever seen. For one thing, when you look at it, your first question is, where are the craters? This is an asteroid. Where are the craters? It's a 500-meter asteroid. So this is 500 meters. So it's small. Well, there aren't easily visible craters. If you look at it closely, you can pick out crater-type features. It also has smooth sections. That's odd. It also has relatively smooth cuts in it. Not cuts in it, but it's smooth areas to it that aren't jagged. So this is thought now to be mostly a rubble pile, held together by its own gravity. A really, really strange object. And so some of the things that make up the rubble piles, jut out. And sometimes it gets hit by something that does leave something like a crater, but it's just stranger. Okay, more recently, since, well, the course almost started, the Rosetta spacecraft out in the solar system with the European Space Agency, which is headed toward a comet, I'm going to get this name wrong, Churyumov-Gerasimenko. It should get to that comet in 2014. But along the way, they buzzed it past this asteroid Steins. And so it took pictures of it. And here's 6 images. And I don't see a size for it. It's unusually shaped. It's like a diamond. And it happened just recently. So we're getting close-up pictures just recently of asteroids. There are other strange asteroids in the solar system. This one is co-orbiting the sun with the Earth, but not in a simple way. The moon sort of co-orbits the sun with the Earth, but that's in a clear orbit around the Earth. This one maps out this, as the Earth goes around the sun, maps out this strange yellow orbit. And it's called asteroid 3753. So we didn't guess that this existed, but we found it. And it trails the Earth in a strange way. So given Newton's gravity, there are strange ways that things can orbit around the solar system. Okay, asteroids in the distance. Here's an asteroid that was found with Hubble Space Telescope, this big blue streak. It was found as the streak. Will things hit? It turns out that things hit Earth all the time. They're usually just too small to make a difference. So people are worried, oh no, one day a big rock will hit Earth. Well, rocks hit Earth every day. The question is, how long do we have to wait before there's a rock big enough that hits Earth that causes damage? So all the time, little space debris is so small, sand-sized stuff, is coming to Earth and causing meteors, which we'll talk about next time. And they're flittering down to the surface. So there's a small amount of stuff always flittering down. There's big rocks, bigger sand-sized things that cause streaks in the Earth's atmosphere called meteors. And there's rocks that hit every now and then, and we find them in Antarctica. And they not only hit Antarctica, they hit everywhere. But they're not always washed when they hit. And so we don't always know. So they're just mistaken for regular rocks, and they're hard to tell from regular rocks. We're worried about the big stuff. How big is it? Depends. Its mass is also important. If it's fluffy, like a rubble pile, it might not be that important because it doesn't have all that much mass. If it's dense, like an iron meteor, and it's big, then it could be, that's strange. It could be important, and so we're trying to find out about that stuff. So here we see some of the things mapped out as they pass. The red stuff is bigger than a certain size. It's bigger than, and it comes, let's see, it's bigger than a certain size and comes closer to a certain amount of size. So we don't know all that stuff. Here you see this is the Earth as it goes around the sun. So some of these big things are coming pretty close to the Earth. Here you see something that actually passed inside the orbit of the moon. The moon, inside the orbit of the moon, is closer than we're sometimes comfortable with. Many of the things you hear that passed by the Earth, they were well outside the orbit of the moon. But when it gets inside the orbit, then we have to start taking it relatively seriously. This object here, SQ222, passed 1/4 of the distance of the moon. Now, it takes light, light can orbit the Earth 7 times in a second, and it takes light 2 seconds to get to the moon. So that shows you relatively how close the moon is. And the last one is the first one I showed you. This is another picture of asteroid Itokawa. It is just one strange-looking thing with smooth spots and chunky rocks and geometric features on it. And it is still being studied. There's still a mission to return stuff from there, actually. They were going to have something bouncer on it, but the Japanese, that part failed. But just getting close enough to get these amazing pictures is really, really amazing. And also shows that the solar system is now being populated by not just the United States spacecraft launched by NASA, but by spacecraft launched by other space agencies, Europe and Japan and China soon too, and Russia as well. So that will conclude our lecture for today, and next time we will learn about other things in the outer solar system that make visits nearby, comets and meteors.